And the microphone doodad is on, all that good stuff. Cool. Right, so welcome back, guys. So let's see here. In terms of announcements and stuff, your homework will go out probably shortly after class. And then you have, what, about 2 weeks to do it, I believe? The reading assignment is due today, and I believe your project proposals are due tomorrow. Again, they're just supposed to be short. You don't have to go crazy here. Yeah, and then your homework, I don't know. You know, as Sebastian put on a lot of questions, I removed them, replaced them with easier things. And hopefully between the two of us, we've reached a reasonable equilibrium. Any questions about procedural stuff? Cool. All right, so if you recall, the last time I saw you guys, we were talking about curvature, and we're going to continue doing that today. So in our last lecture, we covered some, heuristic is the wrong word, like divided difference style approximations to curvature on polyhedral surfaces, right? And the basic takeaway of a lot of these different methods is that they work well for really finely approximated surfaces, but in the discrete regime, it's a little less clear what they should do, right? Because we're using some kind of Taylor series argument to construct this notion of curvature, but like we're not in a regime that looks like, you know, Taylor series should apply, right? Like these triangle meshes are really coarse. And so today, just kind of imitating the same outline that we had when we talked about curves, right? We talked about divided difference curvature, and then we talked a little bit about sort of the conserved quantity style approach to these things, right? Where you say, you do a little bit of a political, you say, I'm going to redefine curvature on a polyhedral object to be some other number that's related to the one that I care about in the smooth case. And that's what we're going to do here as well, motivated by some of the constructions we already have. Okay, so that's the story so far. And remember, of course, there are two species of curvature that we care about on the surface. Y'all remember what those are? Gaussian curvature and mean curvature, yeah? And so this object here is all furled up, but it has zero, which flavor of curvature? Gaussian curvature, but it does have positive mean curvature. And a surface with negative, or with zero, oh, I already messed it up. But the surface with zero mean curvature can potentially have negative Gaussian curvature, right? Because you can sum them together and get zero out as long as one curvature is positive and the other one's negative, yeah? And so if you have zero mean curvature, what can you conclude about your surface? It's either flat or kind of saddle-like, right, or hyperbolic, yeah? In particular, it can't look like a sphere. Okay. Right, so today we're going to talk about two extremely famous notions of curvature on polyhedral objects, and then time permitting, we're going to start talking about geodesic distances. Okay, so that's our plan for the day. And essentially we're going to talk about one conserved quantity style approach to Gaussian curvature and one to mean curvature. And then, of course, on your homework, what are you going to do? You're going to implement them, yeah? So isn't that exciting? Yeah. So remember from before, one of the big aesthetics in this discrete geometry world is this idea of structured preservation, right? Where you identify your favorite property of smooth curvature. For example, remember the winding number theorem that we talked about for smooth curves. And then you come up with a notion of discrete curvature that sort of preserves that continuous abstraction exactly. Right? And so there's a little bit of a sleight of hand. Oftentimes, maybe the thing when we talk about structural preservation is really kind of just by definition. But at the very least, we have some notion that resembles some object that we care about in the smooth case. And then the mythology is often that sort of if you discretize things in a structure preserving way, then even if you have a pretty coarse approximation of your geometry, the measurements you make are still somewhat reasonable. And that's mythology. I mean, right, there's no math there. Or there is, but you have to be precise when you say stuff like that. Okay, so unfortunately for us, the structure that we're going to preserve is one that I'm going to have to state and not prove because it's typically the crowning result of an undergrad differential geometry course, which is something called the Gauss-Bonnet theorem. So the basic idea of the Gauss-Bonnet theorem, and we're going to see that the discrete Gauss-Bonnet theorem is extremely easy to prove, although the smooth one is quite difficult. So the basic takeaway of Gauss-Bonnet, by the way, you know the little slogan on the cover of the textbook by Spivak? There are these people like marching down a very hippie-looking hill with differential geometry operators flanked on their sides. This is all the way with Gauss-Bonnet on this little ribbon that's like flying over their head. It's really cute. You should look up this textbook cover. But in any event, the Gauss-Bonnet theorem, in fact, maybe even ignore the boundary term for now, says that if I sum up the curvature over an entire surface, this thing is a topological invariant. It actually counts the number of holes, or in this case, the Euler characteristic, which is related to the number of holes, scaled by 2 pi. Yeah? This is a little bit of a surprising fact if you think about it, right? Like what it's saying, like think about if you have a sphere, so a two-dimensional sphere would be like a circle. Notice, by the way, that this kind of looks like the winding number theorem in some very rough way, where you have 2 pi times some topological invariant is like the integral of curvature. This really is the higher dimensional kind of version of that, right? So think about, so if a sphere is the surface of revolution of a circle here, just before I got here, I was reading on Stack Exchange how people think about this theorem, and actually the explanations are remarkably useless. I was pretty disappointed. But one of the ones that somebody drew that at least kind of helps you think about it a little bit is like if I took the top of a sphere and I like kicked in some dimple like that, and then I took the surface of revolution, right? What did I do? Well, I added some piece of the curvature, some piece of the surface with some positive curvature here. Right? This is Gaussian curvature, so remember the direction of the normal doesn't matter. But then in exchange for doing that, this piece is going to look hyperbolic, right? If I rotate this out of the board. I know I'm asking for a little bit of mental spinning going on here. Yeah? And that's roughly what this theorem is trying to say, that if I add a piece with some extra positive curvature, I have to pay for it somewhere else with some extra negative curvature. Of course, actually checking that is quite different from drawing a little dimpled sphere, and because the definition of Gaussian curvature is a little bit involved, you can imagine that checking this is a bit of a headache. One additional thing worth noting is, of course, there's an additional term here, which is an integral over the boundary, right? So if I like puncture the sphere and it has some one-dimensional boundary in it, then I have to account for the geodesic curvature of that boundary piece. We're actually going to use that in a second. I realize that this is extremely fishy, high-level explanation of a crowning result in geometry, but in this course we have to make some trade-offs. Yeah? Okay. I should have put that book cover there. It's super cute. Yeah. Oh, so G is the genus. So if I'm going to get this wrong. If I have a donut, then the genus is 1 because it's got a hole in it. Is that right? I'm looking at Ed. Yeah? I always get these things backward. So genus is the number of holes if you ignore your boundary. And so this is 2 minus 2 times the number of holes. And that object is called the Euler characteristic. And I think roughly it's because it shows up a lot in topology. Obviously, you could have written it in terms of G. Yeah. Oh, you're absolutely right. I'm sorry. Yeah, you're absolutely right. There should also be a minus n, where the n is the number of boundary loops. In fact, let me. Great thing is, we can fix it.
The Euler characteristic is 2 minus 2g minus n?
Yeah. Okay. Sorry. That's we're often one thing that you'll see in research papers in this field is that we all get boundary things wrong. This includes your instructor and some of his published work, which he's less than proud of. Okay, so in any event, the good news is that the discrete versions of these things are much easier to think about than the smooth ones. And so let's jump to that picture instead. Right, so let's say that I have a polygonal cell on some triangulated surface, and I want to know the integral of Gaussian curvature over the cell around a vertex. Okay, that's my goal here. Yeah? And in particular, I'm going to define an object called the Voronoi cell of this vertex, which is the locus of all points on the triangle mesh, which are closer to this vertex than to any other vertex. Okay? So one thing that you can double check is, for instance, obviously the Voronoi cell of this vertex hits this edge in a particular way. Anybody remember anything about high school geometry, where like how it hits this edge? At a 90-degree angle, the midpoint. Okay. So these are all things that you can double check. But this, remember when we talked about integrating a function on a surface, and we had to sort of say like, well, if I have a value here, how should I interpret it, right? And one thing I had to do is kind of multiply it by area. This is one reasonable notion of area around this vertex, which is sort of consistent with some nice curvature theory. Okay? All right, so let's say I want to integrate curvature around this cell. One way to do it is actually apply the Gauss-Bonnet theorem, and then we're going to kind of apply it backward a little bit. Okay, so one thing to do, this is we're going to take that boundary integral term. So first of all, the Euler characteristic in this case is just 1, yeah? So you get 2 pi. And now, and remember when I say Euler characteristic, I mean of the cell, not of the whole surface. Okay, and all I did was subtract off that boundary integral term. Yeah, and now I'm going to do a little bit of a discrete trick, right? Because, well, remember we already talked about how to get the total curvature of a curve when I go around the loop, right? One way to do it is to just sum up the exterior angles of a loop. Yeah. First of all, you guys should be totally suspicious of me right now. I mean, I've drawn this as a flat object, but really this is a mesh on a 3D thing, right? Like these vertices and might not all be on the same plane. Why is that okay? Something really sneaky happened here. So this is geodesic curvature. Remember, geodesic curvature is the component of curvature in the tangent plane. What happens, so where does curvature happen? Well, it's flat, 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 and then there's a turning angle. Does geodesic curvature actually see the dihedral angle here? Does it see the angle between the two triangles? No. Right, because when I unfold this thing, it's just a straight line. Yeah? And so actually this truly is the proper notion of integrating curvature in this cell, is just summing up the exterior angles, these epsilons. Okay, so let's do the world. So now let's do a geometry diagram that I am confident I can do in class here. So I'm going to draw you a particular polygon, which is this epsilon and this theta here. Okay, so we have there's theta. These meet at 90 degrees, like that. Right? These are the Voronoi dual edges, so you can kind of convince yourself they've got to hit right perpendicularly, if you haven't seen it in geometry class. And then there's some other angle, and if I extend like that, I get this epsilon angle here. Okay, what is this angle? Oh, come on. In terms of epsilon. Thank you. Okay, so what's the sum of all the angles in a quadrilateral? 2 pi. What's 2 pi minus pi over 2 minus pi over 2 minus pi minus epsilon? Epsilon. Yeah? Okay, so what does that tell me? That tells me that if I want the curvature at this vertex, what's a different way that I could get it? Like, these are kind of weird angles to draw on a mesh, but what did we just show? It's the same as summing up all the interior angles adjacent to the center vertex. Okay? So this is starting to look nice, yeah? So in other words, here's our alternative formula for curvature. Let's do a few sanity checks here. Okay? So let's say that I have a planar vertex. Here's one, because it's on the computer screen. Yeah? What's the sum of all of the interior angles adjacent to a planar vertex? We're going to use all of our favorite high school geometry facts today. 2 pi. What's 2 pi minus 2 pi? 0, not 2 pi, whoever said that. That makes some sense because the screen is flat. Yeah? So what does it mean if this number is positive? So if this number is positive, then there's sort of less theta than 2 pi. That make sense? So think about the picture you should draw in that case. Let me see if I can reenact it with a sheet of paper. I'm going to fail. Is like taking the angle at this vertex and kind of sucking it in like that. What happens to this cone? Well, it becomes more pointy. Yeah? Have I managed to lose you all yet? Do you see what happened here? So as I tighten the amount of circumference that I have around this point, the cone becomes more conier. Yeah? It becomes sharper. And similarly, right, if this number is negative, right, I have a negative curvature vertex, one way to think about that is there's excess angle here, which means that this object kind of has to buckle. Yeah? And that's what makes it into a hyperbolic thing. Yeah? And so at least the sign of this curvature value makes some sense. Right? Because remember that zero curvature means flat, positive curvature means looks kind of like a sphere, negative curvature means looks kind of like a saddle. Yeah? So that's all that's going on here. So of course, what do we do in discrete differential geometry? We turn around what we did with like a pseudo proof. Right? This was definitely a pseudo proof for any number of reasons, but probably the main one was that I didn't actually take the integral of curvature. I kind of summed up angles and invoked our old discrete notion of curvature. There is some relationship, but we haven't done it carefully. So one thing we can do is flip it backward and say the discrete integrated Gaussian curvature at a vertex on a mesh is just the number that I sort of motivated on the previous slide. Yeah? And at least we know that the sign kind of makes some sense. What do I say integrated? Well, let's think for a minute. So what happens if I take a triangulated surface and I refine it, right? I make denser and denser triangles. Yeah? Then what happens to all the triangles around a vertex? They start to just look flat, right? And that makes sense because when you add up the thetas, you're going to get something close to 2 pi. Right? So clearly that number has to do with resolution, so you kind of have to cancel it out by dividing by area. Yeah? And yeah, so this object is the discrete curvature of a vertex. And now, sort of tautologically, we can prove the discrete Gauss-Bonnet theorem. Yeah? So let's do that real quick. So remember from a few lectures ago that a different way to obtain the same Euler characteristic is to take vertices, the number of vertices minus the number of edges plus the number of faces on a mesh. And as long as it's a manifold triangle mesh, we're going to assume no boundary because I'm going to get it wrong anyway if there is one. Okay? And this corresponds to our sort of different homology donuts that are available here. Yep. Okay, so we additionally to that, in fact, I think it was even on your nano quiz, proved a few little corollaries to this formula, right? So one of them was that 2 times the edge, in fact, this isn't even a corollary of Euler's formula. It's just a simple thing to notice, right? That 2 times the number of edges on your mesh is equal to 3 times the number of triangles if there's no boundary, right? Because every triangle has 3 edges, and every edge is adjacent to 2 triangles. Yeah? And remember what we did is we plugged in that little thing in the bottom right into Euler's formula to make a slightly different relationship, right? Like you can eliminate either E or F, depending. Okay, so that's all we're going to need for discrete Gauss-Bonnet. Okay, in particular, let's say I wanted to take the integral of Gaussian curvature over the mesh, right? I mean, that's roughly what the Gauss-Bonnet theorem is trying to do, yeah? It's integrate Gauss curvature over a surface. Well, one way to do that, of course, is to sum over all the vertices and add up their integrated curvatures. Yeah? Okay, and now we have a definition. Yeah, so let's plug it in. Right, so here theta ij, the j would be like the neighbor of theta I, right? And the I would be like the center vertex. This is sloppy notation because it's like not going to matter in a second. Okay? And so this is just the definition we had a few slides ago, summed over all the vertices. What are we going to do next? This is one of these, like I had a math professor in college that always say, like, it's important not to think here. Like there's only one thing we can do, right? We have a sum, it's parenthesized a particular way. Let's move the sum inside. Yeah? So first of all, what's the sum of 2 pi over I? Yeah, it's 2 pi times the number of vertices, right? Because it's 2 pi times the sum of 1 plus 1 plus 1 plus 1 plus 1. Yeah? Okay, so that's good news. So let's plug that in. This is starting to look like Euler's formula, huh? Okay, and what is this quantity here? Well, let's think for a second. What's going on here? This is summing over every vertex, right? And then for every vertex is looking at all of the interior angles adjacent to that vertex and summing them up. Yeah? You see that? So like in particular, if I have a triangle mesh, like here's a vertex, right? So this would be like the sum of all of these angles, yeah, and then maybe this vertex, I also sum all of his angles. Somebody has a Facebook message, and so I get this thing, and then maybe this vertex, so I get all his angles, yeah. Notice I drew this in a suggestive way. That by doing that, I ended up summing up all the angles in this triangle here. So rather than summing over vertices, I could sum over all the triangles. And what's the sum of the interior angles of a triangle? Pi. Everybody repeat after me. The sum of angles in a triangle is pi. Yeah. Okay, great. Yeah. So, right. So at the end of the day, this is the expression you get, right? Because it's pi times the number of triangles. Killing me. Okay, so at this point it's just algebra. Yeah, so I can factor out pi, and by Euler's formula, that's 2 pi times the Euler characteristic. And there you go. You have discrete Gauss-Bonnet. Yeah? So it's just an application of the Euler formula we had before. Yeah, so this is a much simpler notion, and indeed, as with our notion of, seriously guys, put your phones on mute. It's just an application of the sort of simple topological information we knew about simplicial complexes that got us to this formula here. Yeah? Even though we kind of motivated the formula up there by taking a little boundary integral. So it's nice to know there's some order in the universe. Well, what haven't we checked about this notion of curvature? Well, for one, that has anything to do with curvature, right? And in fact, that proof is much more involved, right? To show that, like, if you take this thing divided by the area of the cell and take some limit as you refine the mesh, that thing really gives you Gaussian curvature. And those are really hairy those are really hairy mathematical proofs, right? Because you have to define what does it mean to take a limit in this regime, right? You sort of have this sequence of triangulated meshes that gets refined, right? And for example, the case to think about that would be pretty pernicious would be like, here's a triangle, and here's another one. Actually, it's not unlike some of the diagrams Lorenzo draws in my office. Well, here's a way to subdivide it. Here's another way to subdivide it, right? Somehow all the triangles, the areas are going to 0, the edge lengths are getting very small, but the convergence is unlikely to hold in this sort of regime, right? So defining convergence in this case is actually pretty tricky, and something that people think about a lot. But not in this class, because it's hard. Yes?
So, in that sigma, what is wrong with doing like number of vertices times 2 pi?
Number of vertices times 2 pi.
To do the summation?
You mean here?
To do it, it's probably 2 pi times v, but it's wrong. Because like, at every vertex, you have a 2 pi around it. Oh, okay. I'm wrong.
Okay. Any other questions? Fabulous. Okay, so now we have a discrete notion of Gauss curvature with some conserved object, in this case the Gauss-Bonnet theorem. Right? On your homework, when you guys implement this thing, if you choose to, I think we said take any 2 Gauss curvatures and implement it is what your homework says, and compare. I encourage you to try this one, mostly because it's easy. Right? At the end of the day, it's just summing up angles. And if you want to debug your code, the easiest way to do it is like literally just sum up your curvatures and make sure you get the right value. Yeah? Okay. So that's a notion of Gauss curvature. Now for structure preservation for mean curvature, it's a little bit of a trickier story. We haven't talked about much. But we did define one kind of fun fact about mean curvature, which is it sort of gives you the gradient direction in terms of how to flow your surface to decrease the surface area. Right? That's one notion of mean curvature, right? Is that the mean curvature weighted normal is the direction to do gradient descent on surface area. Okay. And here's yet another kind of visualization of what this looks like, courtesy of my colleague at CMU. And you can see that minimal surfaces they tend to have this like kind of potato chip look to them. And these are all objects where what I did is I fixed the boundary. Keenan fixed the boundary, which are these black curves, and then just let surface area decrease until it couldn't anymore. Yep. And if these things look like bubbles to you, that's not a mistake, right? This really is roughly the physical process that goes behind forming a bubble object. Okay. Right. So if we want to define mean curvature, or at least the mean curvature normal of a triangulated surface, this is actually a pretty reasonable starting point, right? Because a triangle mesh has a perfectly well-defined area, right? In fact, in a sense, that's much easier than most of the stuff we talked about, right? The area is just some function that takes the list of vertex positions. Implicitly here is the connectivity of the mesh, and outputs a number. Right? What is that number? It's just the sum over all the triangles of the area of the triangle. Yeah, and that's a well-defined function. It has a gradient, and so that gives us some toehold into computing a notion of mean curvature on this dolphin here. Notice it's kind of an integrated mean curvature, by the way, because if I move this vertex, a lot of other stuff on the mesh moves with it. Yeah. Okay. So let's do that. And this is a fun calculation that I like to screw up. So let's give it a shot. Okay. So the first thing we're going to do is we're basically going to apply a lot of just high school kind of trigonometry to taking the gradient of the area of a triangle with respect to one of its vertex positions. I think this is actually a formula that many people really haven't seen, but it's a great way to motivate some trigonometric stuff that you probably just memorized in 10th grade. Yeah, so in particular, we're going to set up a coordinate system that's convenient for us. So here's a triangle. Okay. We're going to set up a coordinate system. Wait, stop laughing. Okay, so here's one direction is E. My coordinate system is going to have unit length. Okay, so I'm just going to, for convenience, I'm going to rotate my triangle so that the base of my triangle is aligned to my first direction. My second direction is going to be up. Believe it or not, these two vectors have the same length. This is E perp here, which I put downstairs. And there's a third direction because this is actually a 3D triangle, which you might not have realized. And that faces out of the board, and that's N. Okay? So, first of all, let's say that the gradient that we're going to take is respect to the position of this point P. So anybody have any good intuition? Where do you think this direction points? Everybody point your fingers in some direction. Where do you think that the gradient goes? There's some disagreement. Good. So let's do some calculation and find out. Okay. Right. So first of all, what are the coordinates of this point P? Well, it's the normal component in the normal direction plus the edge component in the edge direction plus the perpendicular component in the perpendicular direction. Haven't said anything too profound yet. Okay. And I'm going to label, just for fun, I'll label this distance B for base. Yeah. So what is the area of the triangle? Come on, what's the area of a triangle? Yeah. Nope, no trigonometry allowed. I already gave you all the annoying part. Yeah.
1/2 base times height.
Yeah, and conveniently we know the height. Yeah, because I gave you coordinates. Yeah, so it's 1/2 times the base. Well, the triangle's sitting in the plane, so this coordinate is 0. So it's just right. It's the area of the triangle. 1/2 times the base times the height. Okay. But now we can think of this as sort of a function of, oh my, I'm sorry, I'm an idiot. What I meant to say when I said the height of the triangle, hi, this is not off to a good start. Right, so we're going to ignore this formula I wrote here and backtrack a tiny, tiny bit. So what is the height of the triangle? Well, it's the component. So what is this vector? It's the component orthogonal to the E vector. Sorry, I summed up the wrong objects, right? So it's really P n squared, not this guy, because the base is being left alone. I'm only moving P. Yeah? Like that. My apologies. Have I lost you guys? Do you guys agree this is the area of the triangle? Whew. Okay. Right. So at this point, I think this is still high school math. Now let's bump it up to, what, 11th grade, 12th grade, 10th grade, because you guys are MIT kids. And take the gradient of this thing. Yep. So first of all, what is the area with respect to the component in the E direction of P? Does it appear in this formula after I fixed it? No. Yeah. Okay. What's the? We'll do it in the N direction. Well, this thing. Let's see here. Well, remember we have this formula for the derivative of the length of a vector we've talked about before, right? So this ends up as the base, right? Because that's just hanging out there as a constant, times Pn divided by the square root of that stuff. Right? Because remember the derivative of the length of a vector is just 1 over the length times the derivative of the stuff on the inside. Yep. What is this? What's Pn when in the place where I'm differentiating? 0. It's in the board. See, now you can see why I chose the sneaky coordinate system. Okay, and then what I'm left with is one additional expression. Oh, there should be a 2 there. Not that it matters. Yeah. Okay, and then finally we have dA dP perp. Yeah, and of course this thing, Well, the b is a constant. You get this thing over here divided by 2. This is just the chain rule. Yeah? Okay. Can I say anything about this number? No, it's a number. Yeah. Okay, fabulous. But let's think for a second. What do these three expressions tell me in general, right? I just took the gradient of area with respect to p, yeah, and two components of that are 0, right? The e component, so like the horizontal one, the n component, which comes out of the board. So what's left is just the component in the board. And this makes sense. So essentially what it's saying is if I want to increase triangle area the most, I should take p and move it up. Okay? By the way, it's only true to first order. If I took the second derivative, then like coming out of the board would obviously matter. Okay. And so this is the picture we should have in mind, right? That and furthermore, look, you have a 1 over length factor there, which is kind of nice. So what do you get? You get that if p is in this coordinate system, this is our formula for area we had before. And then what we get, we now have one additional piece of information, which is the gradient of triangle area is 1/2 times b times e part, this vector facing out. Okay. So now we're getting in good shape. Yeah, we're starting to be able to fill in a little bit of our picture. And so the question is, well, what is the length of this thing, right? That's what we need to compute mean curvature. Okay, so now let's do a few more kind of trigonometry fun facts here. Anybody know the ratio of the base to the height of a triangle? This was a new one to me before getting in this little research field. It's a really easy one, actually. So here's a nice picture. By the way, I revised my proof of this formula, so there's some chance that somewhere in my cotangent derivation there's something wrong, but I don't think so. Okay, so the base divided by the height of the triangle, I can take the base and divide it into the length on one side of the base plus the length on the other side of the base. Yeah? Okay. Well, so if I distribute the sum, this is L1 over H. Well, look, I have a right triangle here. This is where my old proof went wrong, because it turns out that adjacent over opposite is what? Cotangent. My old slides for this class had tangent, and that's my bad, and I canceled it out with a typo later. And then similarly, L2 over H is cotangent of beta. Yeah? So fun fact, if you ever needed a use for the cotangent function from trigonometry class, you have it. It gives you the ratio of base to height of a triangle, which is going to be handy for us in just a minute. Okay. So now we're getting there, right? We're starting to assemble all the pieces of our gradient formula. Okay. Up next, we're going to say, okay, so now we know something about the aspect ratio of the triangle. What can we say about this actual red vector that I've marked here? Yeah? And in particular, remember that I kind of want to write everything in terms of that vector p, like the position of the point at the top. Let's think about that for a minute. So let's say I have a triangle whose vertices are p, q, and r, like I've labeled here. And I want to know a formula for the vector h. Okay, so how could I do it? Well, let's define a new vector p naught, right, which is just sitting right underneath p, kind of projected down onto the bottom part of the triangle here. Okay. This shouldn't be obvious if you eyeball it. There's like one step that's missing here. Okay, so all right. So right. So here's our triangle, and this is p, q, r. I have an edge like that. This guy points up. Here's h, and this is p0. Okay, that's our scenario so far. So one way to do this is just to start labeling some additional lengths that are going to be useful. So here's L1 and L2. Okay? So one way to understand P0, well, he's some fraction of the distance on the line from Q to R, right? So he's Q times some number plus R times some number. Yeah? Okay, so let's do a sanity check. When he's all the way over to the left, like he's sitting on top of Q, right, then L1 is going to be what? 0, yeah? So then it better be the case. That is L2 divided by, I always get that backward. Yeah. And similarly, this is the fraction of the way that you are in the other direction. So let's, cool? Did I do that right? I did. Okay. So one thing I can do is just take the top and bottom of these fractions and divide them by the height of the triangle. Yeah? So this is L2 over H divided by L1 over H, L2 over H. Okay. And why did I do that? Well, let's label this angle alpha and that angle beta. What do I get? Well, what's L2 over H? Again, that's adjacent over opposite. So it's cotangent of beta. Yeah, so this is, and this is cotangent alpha plus cotangent beta, right? Because it's the other ratio. Hopefully I got that right. I did. Oh, good. And similarly, right, this is just the opposite. Cool. So then that justifies the formula on the screen here. Okay. This is like the only area where cotangent is like the most common trigonometric function. It's kind of nice. Okay, so now what are we going to do? We're going to compose all these different formulas together and make one final thing for the gradient of triangle area with respect to vertex position. So here we go. So the gradient of triangle area with respect to vertex position, we already showed it was that from before. Yeah? So I'm going to divide by the height and multiply by the height. Yeah? Because E perp, of course, is really the height vector divided by its norm. Does that make sense? Because height is perpendicular to the base. Okay, well, okay, so what is base divided by height? Remember, we proved that that's the sum of the two cotangents. And similarly, the height vector we just showed is this funny thing. Okay, so what's going to happen? If I multiply out, then this guy disappears, and P inherits a cotangent factor. And then I end up with this nice formula here. That makes sense? I always get suspicious of whiteboard, of computer screen math, but I think in this case we're okay. All right, so first of all, let's step back and look at this formula for a minute. It's a little bit surprising. What happens if I triple the size of my triangle? Well, like if I scale my whole triangle up, notice that this thing kind of scales linearly because of the positions of the vertices. But what doesn't change is this cotangent factor. Right? And so it's very easy to kind of separate out the effect of scaling versus the effect of angles, and that's actually not a mistake. And we're going to see that come up later when we think about Laplace operators. Yeah. Of course, we went to all of this work, and at the end of the day, this is the gradient of the area of one triangle with respect to one of its vertices. So now what are we going to do? Well, remember the area of a mesh is really the sum over all the vertices of the mesh, over all the triangles, rather. Yeah? And so in particular, if I take the gradient of area of the mesh with respect to a mesh vertex, I've got a sum over its one ring, right? That's all the stuff that changes as I move that vertex. Yeah? So unsurprisingly, the formula looks a bit like this, right? Where you just take the inner part of that sum is what you just showed, right? Summed up over all the different neighbors qj. Cool? All right. I see a hand. Yeah. Oh, well, it's 100% accurate. This is the formula we just derived it. Yeah, there's nothing inaccurate about it. Yeah. So the cotangent, let's see here. So cotangent has an asymptote when you have a tall, like a slivery triangle, right? And that's sort of the case when you really shouldn't be doing mesh processing anyway. We'll come back to that anyway. So it's unstable when your triangle is nearly zero area, like it's very flat. But that's sort of what you would expect, right? It's like, remember in your last homework, you took the derivative of the length of a line segment, right? And you got that it was a vector pointing this way, but with unit length. And somehow that was a little unstable. Like when you did curve shortening flow, if you had like a joint like that, but only slightly, it would want to flip way down. There's something similar happening here. Yeah. Any other questions? Yeah. Oh, I'm sorry. There's a bit of a sleight of hand that happened here. Yeah, great question. So remember that I took the gradient by summing over the one ring of this vertex. And let's say that I took the gradient of this area with respect to this vertex. I would get two terms. I get this edge weighted by that cotangent, and I get this edge weighted by that cotangent. But then this edge also appears in this triangle sum, right? But this time weighted by the other cotangent. So essentially all I did was I flipped the inside out. I counted over edges instead of over triangles. Yeah, good catch. Any other questions here? Sneaky stuff. So this is one of these formulas that's going to come up over and over and over and over again in this class, and it's really surprising. This is the first time that you're going to see an object called the cotangent Laplace operator, although we haven't told you it's the Laplace operator yet. Okay. Right, so if you want, yes?
This is a scalar function.
This is a vector.
This is a vector.
This is the mean curvature normal. It tells you how to move the vertex to increase area.
But we can get a mean curvature normal, we can get a Gaussian curvature. But this still doesn't give us a principal direction.
It does not give you a principal direction.
Okay.
Yeah, and as far as I know, there aren't too many works out there that try to do structure preserving principal direction. Yeah, it's a good point. I suppose you can get it as a function of those two things. But there's, it's a little bit tricky because they live in different places too. Yeah, I'd have to think about it. I don't know. Yeah, this is a good question. Yeah, these give you mean and Gaussian curvature. They don't give you principal direction. Let's think about it. But in any event, again, we can flip things backward. Remember, we got the mean curvature normal as by taking the first variation of surface area. Here, we took the first variation of discrete surface area, so we're going to define this thing to be the discrete mean curvature normal. And indeed, this actually is a pretty reasonable way to compute the normal of a triangle mesh. It's just to apply this formula and then divide it by its length. It's a little bit unadvisable in practice. Why is that? Where does this formula break down if what I really care about is the normal direction?
Flat.
Yeah, when the surface is flat. Yeah. Of course, there's a much easier way to get the surface normal if your surface is really flat. Yeah. So, yeah. You're looking suspicious. The easy way to get the normal of a surface when it's flat is to take the normal of any of the triangles adjacent to the vertex. Yeah. This will agree. Well, this is the mean curvature normal, so it'll be 0 because flat things have no mean curvature. Yeah. Okay. Right, so again, this gives us an integrated mean curvature normal, right? Because as I move that vertex, that entire one ring worth of triangles is kind of moving with it. If I want the discrete one reasonable thing to do is kind of divide by the area of the cell nearby. And this gives us an h and a k per vertex on our mesh. Yep. The nice thing is they conserve some amount of structure from the smooth case. Okay, is this the only formula? Of course not, right? There are many formulas out there, and for example, one thing that you see show up a lot, especially in the physics literature, is the notion that somehow really mean curvature sits on the edges of your triangulated mesh. That makes some sense, right? Because if you think of a mesh as sort of a piece of origami, right, then sort of when you bend two triangles that hinge about a shared edge, that entire hinge angle really is just mean curvature, right? Because there's nothing about the distance that senses that kind of motion. Yeah, and so that's one way to do it. This is so. For instance, here they talk about the integral of the mean curvature over some cell around an edge, and I've included a pointer in the slides to this if you guys are curious. One challenge here is, well, this associates a mean curvature to every edge. Maybe you use our old formula and you have a Gaussian curvature to every vertex. Not totally clear how to combine those things. Right? One additional challenge of this particular formula is that edges are oriented every which way, right? And it could be that like a surface is kind of bent in one particular direction, and if the edge isn't aligned to that direction, this formula is kind of a weird thing to think about. Yeah. Yeah. But anyway, I've included all kinds of pointers to other curvature measures in the slides. You guys should take a look at these papers just to get an idea of the amount of work people go into engineering these things. For example, there's some that have to do with, tuned for variational applications. Like I want to smooth out a surface, so I really care that my curvature is somehow a good proxy for smoothness, or maybe I have a noisy surface, so I want to take a larger neighborhood around a vertex instead of just the one ring, and compute curvature that way. This is, in some sense, a weird thing to think about, right? Because remember, curvature is a derivative. You shouldn't need more than a tiny amount of local stuff. But on the other hand, if you kind of fit a surface to a bigger ring, maybe you get a more stable measurement. There are all kinds of strategies out there, and essentially, I mean, even this year, I think we were reviewing some papers that proposed different curvature methods, measures on discrete things. Some other strategies you see out there include like fitting a little surface to some ring around a vertex and then using the curvature of that surface as kind of a proxy for curvature at that point, or grab your favorite formula for curvature and discretize it somehow, or of course the latest thing is to try and learn that function. Which is easy to laugh at, but actually if you have an extremely noisy surface, you could argue that there's a little bit of an inference problem hiding there, which is that like the point sample that you have when you run your 3D scanner is not totally accurate, right? And so maybe you're kind of inferring the smooth curvature of this surface that you don't really have access to. I would argue that's a little bit of a weird thing because curvature has a well-defined mathematical formula. So at that point, you might as well just look at the application you care about and maybe learn something downstream. Yeah, but I don't know. You convince me I'm wrong. So my practical advice, of course, is try as many of these things as you can. None of them is particularly hard to code, right? I mean, they're annoying to derive, but at the end of the day, these are just formulas in terms of angles and cotangents and cross products and things. Yep, and you'll see that on your homework. Okay, so that's curvature. Any questions about that before we move on to distances? Fabulous. Okay. Right. So let's flip onto the next deck here. Did I post this on the webpage? I think I did. I intended to. Okay. So our next topic in 6838 is computing geodesic distances on a surface. These are shortest paths between 2 points where the restriction is that your path must move just along the surface. Yeah, you see a lot of 3D models of this particular guy in different poses because there's a well-known textbook in this area that spends a lot of time talking about fast marching and different algorithms. Okay, so the basic point in geodesic distances, here's a cat, and this cat has 2 feet, actually 4 feet, but 2 feet in the front. And you could ask the question of how far apart are his toes? Do cats have toes? Yes, claws. Well, extrinsically, they're quite close together, right? In fact, if you have these cute cat photos where they're, like that, then they're almost touching, yeah? But of course, if I'm an ant crawling along this dirty cat, then what happens? Well, in order for the ant to crawl from one foot to the other, the ant has quite a long distance to go, right? And so these two notions of distance are just not the same, right? And so the vocabulary word here is that these are extrinsically close, meaning if I consider the space around the cat, these points are nearby, but they're intrinsically farther away, okay? And this is something that shows up a lot, of course. If I want to do analysis on a surface and I'm like trying to characterize distances between the features and all that good stuff, oftentimes it makes more sense to do extrinsic distances, right? So think about like a human tracking application and I'm following the hands, right? There are many poses where your hands are quite close together, but in terms of the body, that's not really relevant. Yeah? Okay. So I think the definition of geodesic distance is a pretty obvious one, right? You take the sort of infimum over all the different paths that connect A to B, and it's just the length. Look at their lengths, and the smallest possible length is geodesic distance. But geodesic distance is an annoying problem, which if you're not used to differential geometry might catch you by surprise, right? Because of course distances in 3D are quite easy, right? You subtract, you square, you sum. But in fact, geodesics on a surface have all kinds of annoying problems. So for instance, one way that I might attempt to define a geodesic, and roughly this does carry through in the theory, is maybe I take, there's a particular diagram that has this cute, it looks like putting in golf, kind of. So I have these 2 flags, and I want to compute the distance between them. One reasonable way to do it might be to take a piece of string, and wrap it around the surface, and then I have a guy standing on the blue flag, a guy standing on the green flag, and they start tugging, playing tug of war, right? And of course the string gets shorter and shorter and shorter, and eventually they're evenly matched. If it's Sebastian, it just keeps going toward him, but the string doesn't get any shorter. And what happens to the length of that curve? Is the length of that curve the shortest path between 2 points? No. No, because it depends on the initial guess, right? This is an example of a problem where in 3D, if we played tug of war, we get a straight line. But along a surface, if I'm restricting that piece of string to only move along the surface, then depending on how I cut around that hole, it may not be the case that when I tug it to a local optimum, I got the global answer. However, it could be for many applications that the local optimum is actually a totally reasonable object. Right? So for instance, what would be a good example? Like maybe I'm just walking along the surface of the earth and I'm looking at my feet and walking forward. It's true that locally, the path behind, the exhaust I leave behind me forms the shortest path. But eventually, I'll go far enough, like maybe I'm walking along a sphere and I wrapped around itself, eventually there might be some other shortest path. Right? And these are all these sort of definitions that in 3D are all the same, right? They don't matter. But on a surface, they're all going to be slightly different from one another. Okay? There's a reality check that we should have before we talk about distances too much. The algorithms that we're going to talk about, well, for one thing, there's my favorite application, my favorite theorem in computer science theory is this one where it's like, if the output of my code changes depending on any one piece of my data, then clearly I have to look at all of my data to run my algorithm, so I need at least order n time. It's like this slightly vacuous statement about life. And there's something similar here, right? The algorithms that we talk about for computing distances are going to require looking at all the triangles, right? They're going to be at least order n, yeah? Probably n log n, like we have some intuition for shortest path. And that's expensive relative to subtract and square, yeah? And so when you look at these algorithms, you have to think really carefully about, like, do I really want to incur the computational expense of computing distances between points relative to just using 3D stuff? And it's a little bit of a toss-up. It depends on the application that you care about. It also depends on the geometry. So for example, on the bunny, 3D distances are kind of a relatively okay proxy for distances between the point if he's like kind of a nearly spherical bunny hump here. Whereas between his ears, that would be a pretty bad proxy. So there's some link there between geometry and the quality of the application, the approximation, all that good stuff.
If we apply that string pooling strategy to a genus zero surface, how would you create?
You tell me. What do you think? So the question let's take a straw poll. So the question was this string pulling strategy. So I will take my lasso, I throw it over across the room. He pulls on the end. We start pulling the two sides of it tight until the string doesn't get any more tight. If I have a genus zero surface, so it's not a donut, it has no hole, does that object give me the shortest path? So let me draw you something, and then I want you to think about whether you should be nodding or not. So let's say I have a surface like this. So I start to add some non-convexity here. Or even worse, let's say that I have a surface, and I put two big hills in it, and I had bad luck, and I threw my lasso around the hill, like that. My hill is really, really tall. And now we start pulling the ends of the hill. This thing is genus zero, right? Maybe it's sitting on the surface of the Earth. Is this string going to give me the shortest path? Unfortunately, no. Yeah. And we know that, right? Like if I hang, here's a counterexample. Here's a piece of string. Here's a hook. I'm a genus zero object, roughly. So I hook this thing and I pull on the string, and it's not turning into a straight line. Yeah. This is true. So in this case, the manifold, I suppose, would be Rn minus my finger. Yeah. In any event, no, the answer is no. Local and global optimal are not the same here. Yeah. Even a better, I'm trying to draw the most intuitive example possible, but I'm a bad artist. Like let's say I have a pancake, and then I make a big hook in this thing. And now I'm standing here, and I throw my lasso, and it goes like that. I think that's the best example. Yeah, and now I pull it tight. Obviously, it'll get stuck. That's better. Okay. But good question. Yeah. Okay. Any other question? Great. Okay. So there's 4 different queries that are all distance related that we'll talk about today and next time. And the kind of funny thing is, they're all the same in 3D, and they're all different on surfaces, which is kind of cool if you think about it. So one is like the locally shortest path. So this would be, like, Pierre is walking back to his office. He's looking at his toes, and he's just walking forward, right? And you look at the trail of string that he leaves behind, as he often does. Twizzlers actually, right? That thing locally is the shortest path, similar to like if you point your toes in a vector and you just start walking, you're drawing a straight line, right? But then what's going to happen eventually? Maybe Pierre is walking along a sphere. Eventually his path is going to meet up on itself, right? And if you look at the whole trace that he drew, that thing is no longer the shortest path between 2 points. So that would be a different query, style query, which would be, the single path, all targets, shortest path, right? This is closer to what we're used to from graph theory. And then there's some additional ones. So maybe I have different source points, and I just care about the kind of closest guy. So like this would be the equivalent of like a Voronoi diagram kind of thing on a surface. Or even all pairs shortest path. We actually won't talk about this in this class. That gets a little tricky. And indeed, there are many different examples. And the funny thing is, all these different distance problems that are all easy in 3D lead to completely different algorithms. So another good one to think about that I think is actually understudied a little bit is, let's say that like I have a 3D model, like I take a 3D scan of Ed, and now I just start poking him at different pairs of points, which is over and over again. And I want to know the distance between these points. So it's a fixed piece of geometry, and I want to amortize over all these different distance queries the shortest path. Right? The question is there a little bit of analysis I could do ahead of time on his 3D surface that might reduce the amount of time that my algorithm takes to compute shortest paths every time I do these queries? Right? That would be yet another example. I only know of one research paper on this topic, and it's not terribly exciting. Okay. Of course, we're all computer scientists here, whether we know it or not, and the typical approach might be, well, this surface is a triangle mesh, right? By the way, most of the algorithms we'll talk about easily extend to higher dimensional objects, unlike curvature stuff. Okay, a triangle mesh has edges, it has vertices, so this thing is a graph. So maybe I use the shortest path along the graph edges, because of course there's lots of code out there for shortest path on a graph. That's the thing that we all study in intro algorithms class. Yeah? How many of us think this is a good approximation? How many of us think this is a bad approximation? Just by virtue of me asking. How many of us think sometimes it's good, sometimes it's bad? Actually, you guys are more or less the right camp. So here's the counter example. Let's say that I give you a grid like this. Notice this is a pattern I can refine as much as I want, right? I can give really, really small triangles that approximate this little patch. Yeah? And I do an evil thing, which is I say I want the distance from this vertex to that vertex. What is that assuming that the edge length of this thing is 1, meaning the whole edge length, rather, what is that distance? 2. What should be the distance? Square root of 2. Yeah, so something went wrong. Yeah? And I can add as many triangles as I want, right? I can densify this pattern a lot, and that number doesn't converge. It's always 2. Do you see that? That's bad news. That means that this approximation, and these aren't bad triangles, by the way. They're nice triangles, right? They're 45 degrees. It's nothing too crazy here. And in fact, it's particularly pernicious, right? Like in one direction, I get it right. I get square root of 2. Yeah. So if I didn't check my code carefully, I might say, great, I got the number I wanted. I'm happy. But then I put in a different query, and that's not the case. Yep. So it's not like one of these things like you just start babbling about convergence and the limit of refinement because I added more triangles and I've got some measurement that kind of looks like distance. That's actually not true here. Yeah. And I think this is easy to get wrong. Yep. Right. This is sort of the difference between L1 and L2 distance. Of course, this is a very particular pattern that I chose for a mesh, right? And there are some notions of like what it might mean to choose random distribution. Like, does the average mesh have this property? And the answer is no. However, for one thing, that's a difficult theorem even to state. But the larger issue is that like these patterns really are pretty typical of what you'll get from a 3D scanner. So it really is something to watch out for. Yeah? Okay. So if we step back, we ask, well, what happened here? It's like everything possible went wrong, right? It was asymmetric and anisotropic, meaning that like squares became kind of rectangular things in some sense, right? And it doesn't go away by adding more triangles. Yeah, this is really quite problematic. Yeah, and yet another way of understanding what went wrong is quite simple, right? If I have two triangles that share an edge, basically what we're missing is that distance. Yeah, and of course it's not just two triangles, right? I could have a whole zigzaggy pattern of triangles like this and want this shortest path. Yeah, so that's where stuff goes wrong. So the first conclusion we should make is, of course, shortest path on a graph doesn't converge to geodesic distance. By the way, what direction does it approach it from? Can it ever be smaller than geodesic distance? No, right? Because you're kind of restricting to a piece of your surface. But it's often an okay approximation. And the reality is that plenty of people, especially in computer vision, make this mistake. And as long as you know it's a mistake, it's often okay. The second conclusion, of course, is that we need some special discretization here to compute geodesic distance. And this is where something interesting is going to happen in our treatment. Unlike curvature, distance along a triangle mesh makes perfect sense. You guys see that? It's just a bunch of triangles glued together, and asking about the shortest path is something you could completely ask. Right? In fact, you could ask that local versus global question, right? You have some polyhedral object, you tie pieces together and you pull, versus shortest path, versus whatever. And indeed, these are problems that algorithm people study. Yeah? One of the things that we're going to see is that actually a lot of the algorithms for computing geodesic distance get it wrong from that perspective. Right? So the most famous one is something called fast marching, which is an extension of Dijkstra's algorithm for shortest path. And the reason is that actually what they're going to do is say, look at the differential geometry of distance functions on surfaces and discretize that in a way that makes the algorithm more efficient than computing the true distance, which might be quite complicated, right? Do you see that like finding this path algorithmically is a giant pain in the tuchus? This is a curved object. and actually, something that I encourage you guys to go home and think about is like, think about the algorithm style question here. Right? Like if I give you a big pile of triangles, I even told you they're linked together into a manifold mesh, and I give you two vertices, can you find the sequence of, you know, the polyline that connects two of them together and has the shortest length? It's not terribly obvious, yeah? In fact, does anybody know the name of the algorithm, or probably the most famous algorithm that does this? What was that? A star. Yeah, A star will do it, but it's a little hard to know about the efficiency there. But there is one with a guarantee that computer science theorists have thought about for some time. It's called MMP. It's the Mitchell-Mountain-Papadimitriou. It's a very famous object in computer science theory, and it's extremely hard to get right. So we'll draw a few pictures of it probably 2 lectures from now, but we're not going to derive it because it's a huge pain. And essentially, what you have to do, just so you can think about it in the shower today, is you have to keep track for every edge of a subdivision of that edge into intervals that all have the same sequence of edge. You know, sort of like this guy went from this triangle to that triangle to that triangle to that triangle. Right, so I'll keep track of the window of all things that have that same sequence of triangles working backward, which is a really complicated object to work with. Yeah?
So it's not NP hard.
It's not NP hard. It's polynomial time, but pain in the butt polynomial time as they go. Yeah. And only recently have people even attempted to kind of code this stuff in a practical way. Yeah. Right. So for today, we'll talk a little bit about the theory of geodesic distance, so we'll probably continue next time, and then we'll talk about algorithms. This is a case where they don't align as well, right? I mean, the nice thing about our curvature picture is we sort of derived a smooth curvature formula and then basically just kind of squinted at a mesh the right way and read it off. Here there's going to be, like, our squint is going to have to happen from a few more feet away to make it work out. But to talk a tiny bit about the theory of geodesic distance, which is enough to fill a half of a geometry course, essentially the main point when you read through at least an intro-level geometry textbook is that there's sort of 3 different notions of geodesic that all, again, agree in 3D. Right? There's the notion of just the globally shortest path, so I look at all the possible paths from A to B, and I want the one with the least length. That's probably the notion that we can all agree should be a geodesic. There's a second, which is a local minimizer, right? This would be this, like, the idea that I throw a lasso and I start pulling, right? And hopefully I've managed with very poor drawing to convince you guys that those aren't the same, even on boring topology object. And then finally, there's this idea of being locally straight, that you just walk in a straight line, and at least for a short period of time, the path that you leave behind you is the shortest path from where you started. And what we're going to find is that all 3 of these things agree for short distances, and then for long distances, they start to disagree. In fact, not start to, like, you'll hit a discrete point and suddenly they'll stop being the same. Okay? Fabulous. So the global definition, just so we all agree on geodesic distance, please don't write this down, it's in the course notes and it's the obvious thing that you would all think of. Right? The distance from P to Q is you look at all of the possible curves gamma that go from P to Q, look at their length, and you take the inf. Right? And as long as you're on a connected object, I suppose I should have stated that somewhere. This is a finite number. Yeah, that's the distance from P to Q. Unfortunately, this isn't a particularly useful definition to work with. Like if you're in differential geometry and I give you a definition like this, you're in a little bit of trouble, right? Because there's nothing differential about it, right? This is saying all the possible paths from one thing to another and minimizing the length. Yeah? So what do you think we're going to do? We only know how to do like 2 things in this class. Take a derivative. Yeah. What kind of derivative? Variational derivative, right? Because we have a curve here. Yeah? In fact, this will be easier than our surface area formula because we're back down to 1 dimension again. Yeah? Okay. And that's our starting point for today. So first of all, remember, this is our formula for arc length. I think we've seen this in calculus class. Okay. So essentially, we're now going to start contrasting those first 2 pictures, right? There's the question of having a globally best shortest path versus a locally best shortest path, right? Remember, one of them is like I can tug on my path and make it a little shorter. Yeah? So obviously, one implies the other, but not the other way around. So we're going to ask the question of what does it mean to be a local optimum, I guess, minimum of length, okay? And that's where our variational derivative comes in, and it looks an awful lot like the one you did on your homework. Right. First of all, there's a little bit of a sleight of hand that usually happens at this juncture in geometry, and I'm going to, out of tradition and mostly laziness, I'm going to do the same. Which is we're going to prove a small lemma, which is that this thing is an annoying thing to differentiate. Hopefully we can all agree on that. You guys have done it now. Yeah. In particular, like this, like think in 1 dimension, right? This object looks like absolute value, right? And it's very rare in calculus class that you differentiate absolute value because it has a singularity point. You get like numerators and denominators. It's just it's no fun for anybody. Yeah. And so what we're going to do is prove a formula out of convenience and then work with that guy instead, and then show that in fact they're the same thing. One thing that's worth noting that often, differential geometry books neglect, we could take the first variation of this thing and we'll get the same formula at the end of the day. It's just more arithmetic. Yeah. So the object that we're going to define is something called the energy of a curve. Anyone who's seen this formula before, by the way, just out of curiosity, the math students. Cool. So the length of a curve is the integral of the norm of the derivative. The energy of the curve is the integral of the norm of the derivative squared. Okay, I mean like that because now when I differentiate this object, I don't get a denominator at least, right? Remember that the derivative of length looks like, or the derivative of the norm of vector, you get a 1 over norm factor there. That's no fun to work with. And so essentially, the theory of geometry, people tend to like to work with this object because the calculations are just easier. And the reason they can do that is because of a nice little lemma that we're going to prove in the next 6 minutes. Okay? Right, and the basic idea here is that there's a relationship between these 2 numbers, right? In particular, that the length squared of a curvature is always upper bounded by some multiple of the energy. And when do these 2 things agree? Any hypothesis? I'll try and stand in front of them. They agree when it's the shortest path, and when that path is parameterized by arc length. You need both of those. But that's actually okay, because we're just looking for some condition, right? And then we have to look back at the geometry and see what happened. But the basic point here, this number is actually parameterization dependent, meaning if I change the velocity I drive along the curve, this number may change. So when I minimize over all possible gammas, the curve may actually shift along itself. But what this lemma is going to show us is that when it reaches that minimizer, it chose among different parameterizations of the curve, right? Like it prefers certain ones over others. But the global minimizer is still also locally minimizes length. I started my way through that sentence. Let's try that again. When I minimize the energy here, I get a specific choice of parameterization for a curve, and this energy does prefer some over others. But we can also say that it is a local optimum of length thanks to this inequality. Whew. Okay, and when we prove that, we'll see that that's the case. Okay. Oh, I just noticed the screen is off. Thank you to whoever did that. Right. So, in order to prove this little lemma here, right, we're going to start by defining something that many of you have probably seen before, which is, let's say that I have 2 different functions, f and g, and they both go from the unit interval into the real numbers. Okay? These are just functions that take in a number, output another number. Then I'm going to define the inner product of these two functions to be the integral from a to b f. Okay? And notice that this is just like a fancy notation for dot product if you haven't seen it before, if you're a computer science student. Right? Essentially, this is saying, like, if f and g are two functions, right, then this is like taking their multiple and then summing them all together over the different t's. Yep. So how many of you guys remember the Cauchy-Schwarz inequality? I'm telling you, we're dredging up all of our favorite boring stuff from calculus class. Yeah? So remember, you've probably seen it for vectors, right? If I take v dot w, what does Cauchy-Schwarz tell me? Anybody remember? Yeah. If you can't remember that this, like in 2D, is mod v mod w times cosine of theta, and the absolute value of cosine is less than 1. Yeah. So Cauchy-Schwarz. In fact, a sneaky way to define cosine would be to, kind of flip this backward, which I've seen some textbooks try and do. So indeed, this formula still works for this inner product, right? This is essentially just a dot product, if you squint. And so, in fact, if I define the norm of f, I guess squared to be the inner product of f in itself, just like the norm of a vector squared is the dot product of the vector in itself. Yeah? Then the Cauchy-Schwarz inequality in this case tells you that this is less than or equal to, that's a g. Like that. Okay? And essentially the inequality that we're showing on the screen here is just a corollary of Cauchy-Schwarz. So let's see if we can prove it. The last time I taught this class, this got a little confused, so I tried to clean it up. Okay. So we're going to start on the right-hand side and work our way left. Okay? So let's say that I have a curve gamma, and I compute 2b minus a times the energy of gamma. Okay, and now let's do a little bit of plugging in here. So, it looks like my notes already have a missing factor of 2, which I will fix later. Okay, so what's a fancy expression for b minus a in terms of an inner product? Well, in terms of an integral. One way to write it. Oh no, my notes are correct. I'm sorry. So b minus a, of course, is the integral from a to b of 1 dt. Okay? And 2 times the energy, that's where the 2 comes from, I'm sorry, I forgot, is also the integral from a to b of the norm of gamma prime squared dt. Okay? Cool? Now this is a pretty complicated looking formula, but why did I write it this way? Well, 1 is secretly a function of t. It's a really boring one, but it is a function of t. Yeah? So this is really the inner product of 1 in itself, in this weird notation that we developed here. And this, so there's a function of t, which is the norm of gamma prime not squared. And this is the inner product of that thing in itself. Cool? All right. Well, okay, so I only have one hammer. I might as well hit some nails with it. Yeah, so if I apply Cauchy-Schwarz to this thing, right, notice these are norms, so now we kind of read it backward. Right, this is like the norm of the function 1 squared. This is the norm of this function squared. Yeah? Okay. Right, so this is greater than or equal to by Cauchy-Schwarz. Cool. This is an application of that inequality up there. Hopefully you guys see that. So, do you see that? Yeah. I think if you read it in this direction, it's slightly easier, right? Because this inequality is less than or equal to, right? This is the norm squared, right? So that's where the 2 comes from. Okay, fabulous. And what is this thing? Well, okay, so let's take a look. So for one thing, you don't really need the absolute value here because it's a positive number anyway. Yeah, so this is the integral from a to b of the norm of gamma prime of t times 1, which of course doesn't do anything, dt. Aha! And this thing is length. Not squared. So you guys see that? So we've shown the first part of our claim on the screen here, which is that 2 times b minus a times the energy, that number upper bounds the length of our curve. A few of you look suspicious. What questions can I answer? What was that? Oh, I'm sorry. Squared. That's squared. I thought you guys meant that one. Yeah. My apologies. Okay. And that agrees with everything. Good. Sorry. Fabulous. So we've shown the inequality. Now we have to show the case where it's tight. Yeah. Right. So let's say that I have a curve gamma of t, and it's the shortest path. But notice that the way that I've written the energy here, my curves have to be from a to b in terms of the parameter time. So I can't say parameterized by arc length unless the arc length just happens to be b minus a, right? So what can I do is I can have a constant speed curve. It just doesn't, the speed doesn't have to be 1, right? So in other words, there's what, parameterized proportional to arc length? P, A, L, something like that. But anyway, so this is gamma of t, and it's parameterized proportional to arc length. A different way of putting that is that it has constant speed, like something like c. We're just going to be lazy. We're just going to call it c. We'll worry about what the value should be later. Okay? Does everybody understand what I just did there? Like, because I've fixed the endpoints in time to be a and b, I can't say parameterized by arc length, but I can kind of warp time a little bit so you're driving with constant speed and you hit the target in the right amount of time. Okay. Fabulous. So in this case, what is the length of gamma? Well, there are many different squared. Sorry, I keep forgetting that too. Well, one fancy way to put it is if c is the speed at which you travel, right, then the length is c times b minus a, right? So this is, let's write it this way, c times b minus a squared, right? Because this is the amount of time you travel, this is the speed, yeah? And of course, now we're going to kind of reverse engineer things. We can say, okay, well, yeah, or actually, we don't even have to do that. I'm simplifying my proof as we go here, which is always dangerous. And similarly, let's start from the right-hand side. What's 2 times b minus a times the energy? Well, of course, this is 2 times b minus a times what? The integral from times there's a 1/2, the integral from a to b times c squared dt. Yeah? And notice what happens. You get a b minus a squared, right? Because there's a b minus a times c squared that comes out here. So this is really, well, the 2 and the 1/2 cancel. You get a b minus a factor there. And then the integrand is c squared. And so actually these two numbers are the same. So what did I show? I showed the following, which is L squared is always upper bounded by this quantity on the right-hand side. And in particular, if I drive along my curve, I'm sorry, this should say by proportional to arc length, my apologies. So if I drive along the curve with constant speed, then these two numbers agree. Cool? I managed to confuse everybody by stuttering my way through that? I think I probably have. But in any event, the basic point here, again, to go back to our logic from before, right? Minimizing this number is kind of annoying because there's an absolute value hiding in there. So instead, we're going to replace it with minimizing the energy. Notice that if I make the energy really small, it has something to do with minimizing length because it upper bounds it. Yeah? And in particular, we have this case when they agree, which is the shortest path. And so we can convince ourselves that when I minimize the energy, I get exactly the shortest, the locally shortest path with this additional added feature that is parameterized proportionally to arc length. Okay, so when we continue next time, yeah, Yue?
Does the speed equal to 1?
No, the speed equals 1 over b minus a. Yeah, that's why I need to reword this slightly. It should be parameterized proportional to arc length.
But from the Cauchy equality,
Uh-huh.
so when it's high, like f equals to b, f equals to g, right?
Yeah, let's see. So you could have applied the equality case for Cauchy-Schwarz.
Then the speed is 1.
Yeah. There's a reason why I didn't do that. I'll come back to you and think about it because we're done for now. Okay. Yeah, some mumbling over there, but I think we'll call it. Okay, guys. So with that, we'll start for the day, and then we're gonna show next time that sort of a corollary of that. Well, for one thing, we'll convince ourselves that when we minimize area, we minimize length. Or yikes! When we minimize energy, we minimize length. Which means that we should take the first variation of energy, and we'll get a nice formula for that. Yeah? In particular, what we're going to show, then I'll shut up, is that if you look at the acceleration of your shortest path curve, what are you going to be able to show? You're going to be able to show that if I take the projection of that object into the tangent plane, remember that has a name, it's like geodesic curvature, that thing is 0. And this makes some sense, right? What it's saying is if I'm driving a car along its shortest path, I shouldn't change the steering wheel, right? But I still have curvature just by virtue of driving over the bumps on the road. Yeah? Okay, so that's what we're going to try and formalize next time. But I think I've confused myself enough for one day. So